Hi, I'm Theo, and now I'm going to present our work on error-free lattice-based key encapsulation mechanism based on Ring-LWE. So this is the outline of my talk. First, I will start with an introduction, introducing some basic notion like what is a lattice, what is a key encapsulation mechanism, and what is the motivation of doing our work. And then we go to slightly more technical stuff on RLWE and cyclotomic polynomials, which is a preparation to go to the main part of the talk, which is the construction of our key encapsulation mechanism, and we end with a brief conclusion. So the big picture is there is a possible emergence of quantum computers, which is a threat to classical cryptography because some problems that were considered difficult before becomes no longer difficult once we have quantum computers of big enough size. And this gives rise to the field of post-quantum cryptography, which is the study of cryptographic scheme that is still secure even if the attacker has access to quantum computers. It has many branches, and one of them being the lattice-based cryptography. So what is a lattice? A lattice can be defined by n factors, which are linearly independent of the real number. So given n factors, b1 to bn, we can define the lattice to be all integer linear combinations of these n factors. So these coefficients are all integers. For example, when n equals 2, we have these two factors, 1, 0 and 1, 2. They are linearly independent. So we have, assuming this is the origin, we have this 1, 0 here and 1, 2 here. What we can do is we can take integer multiples of this point. For example, 2 times this 1, 0 becomes 2, 0, 3, 0. We can have 3, 0, 4, 0, so on. And take the negative multiples like minus 1, 0, minus 2, 0, and so on. Similarly, for this point 1, 2, you can take integer multiples, and you can also take you can also add the 2 points together to get this point, and so on. So the lattice is defined by these two factors, are all these dots here. So they are something discrete. So lattice turns out to be quite useful. It can be used to construct many cryptographic schemes such as encryption, signature, fully homomorphic encryption, as well as the key encapsulation mechanisms, or KEM for short. So what is a KEM? So consider this scenario where Alice wants to do these two things. She wants to generate a random key K, and she wants to share the key securely to Bob. Then Alice can use the KEM because KEM is the cryptographic scheme which is designed to accomplish these two tasks together. So KEM consists of three components. First one is key generation, generates the public key and secret key pair for all users. Then encapsulation with input public key, it generates a ciphertext C and a key K. Then we have decapsulation, where given input secret key and ciphertext, it recovers K back, where K is the one generated by the encapsulation algorithm. So going back to this scenario, and assuming that we have generated the secret key and public key of Bob using the key generation. So what Alice do to do these two things is she calls the encapsulation algorithm with input public key of Bob because she wants to share it with Bob. The encapsulation gives her C and K, and Alice gives K for herself and sends the ciphertext C to Bob. Because Bob has his secret key, he then can use the decapsulation to recover K back. Now, Alice and Bob shares the same random key K. In fact, many lattice-based KMs have been proposed in the literature. However, most of them actually have decryption failure. What it means is that there is a small probability where you fails to decrypt, fails to decapsulate the key correctly. You fails to get back the key correctly. So why is that a problem? Of course, it's a inconvenience because when the two parties thought they share the same key together, but turns out they don't. And what they can do is they can repeat the process again and hope that in the when you repeat the process, you don't hit the decryption failure again. But it turns out that the problem might be a little more serious than that, because Turns out this decryption failure can be exploited using side channel attack to reveal some information on the secret. These are, I just said, some recent works on this attack, exploiting this weakness of having decryption failure. All these attacks arise because of decryption failure, so why not construct an error-free lattice-based KEM? Here by error-free, we mean there is no decryption failure. When you decapsulate, you always get the correct key back. No probability involved. So as with other cryptographic schemes, ours also based on hard problems, and ours is based on the so-called ring learning with error, RLWE. So let's talk about LWE first as a warm-up. LWE, or learning with error, it was introduced by Regev in 2005. It works with factors. So S is a factor, it has n coordinates, and each coordinate is a integers modulo q. Q is a sum prime. This S is usually thought of as a secret. And then we have AI. AI is again, it's the same, similar to S, it's a factor with n coordinates, and EI is a number, is an integer modulo q. EI is sometimes thought of as an error. So then we define BI to be the dot product of S and AI, and then you add TI. So you can write it in matrix notation. This is S, and this is AI transpose. So the dot product is just S1 times AI1 plus S2 times AI2, and so on until Sn times AIN. So the learning with error problem is given a bunch of AI BI. Can you find S? Here the error EIs are not known. You only know AI and BI. Maybe there are a bunch of them, M of them. Then you are asked to find S. And because we have M of them, we can actually, instead of having M equations, we can put them together into one matrix equation. Put all the BIs together, B1 to Bm. This is our S, and this is our A1, A2 up to AM. Put them together in the form of a matrix, and we get this equation, one equation. So this is B equals SA plus E. So I guess learning with error is like, can you learn information about the secret S in the presence of the error E? Because if we assume that there is no error, for example, E equals 0, we have B equals SA. Can you find S given A and B? The answer is you can, because it's just solving linear equation, which is quite easy. But now we have an error E. So can you still learn information about S in the presence of the error E? That's learning with error. So now we go to a variant of LWE called ring learning with error. It was introduced by Lubaszewski, Baker, and Regev again in 2010. Now instead of working with factor and matrices, we work with this ring of quotient of polynomials. So you can think of it as a polynomial ring. So element of this ring looks like polynomial of degree at most n minus 1, where each coefficient is an integer modulo q. It's very similar to LWE. We also have a secret S. S is no longer a factor. Now it's a polynomial. A and E is also polynomials now. And we still have the same equation, B equals SA plus E. The problem is also the same. Given A and B, can you find S? Can you learn information about the secret S in the presence of the error E? We have another variant, which is the decisional variant. So given A and B, decide whether it is generated in this way, or is it just generated totally randomly. So it's distinguishing problems between these two distributions. And we can, in fact, draw some analogy between LWE and RLWE. So in RLWE, we work with polynomials of degree at most n minus 1. So we have n coefficients, E0, E1 up to En minus 1. We can take them together and form a vector. This vector is the one we work with in LWE, and vice versa. Start with vector, you can define a polynomial of degree at most n-1. In fact, you can also define the analogy to matrix, but let's not discuss the details for now. Okay, so in the RLWE, the ring, we actually use a cyclotomic polynomial f. So now let's discuss this cyclotomic polynomials. Uh, it's You can just think of it as an irreducible polynomial over z, meaning irreducible means you cannot factor the polynomial further. You cannot factor them. For cryptography, we actually need another property, which is polynomial need to split into linear factors over zq, meaning when we take modulo q, it actually split into linear terms. Notice that without modulo q, it is irreducible. You cannot factor further, but modulo q, you can factor them into linear factors. Usually f is taken to be of this form, but in our work, we study more options for this cyclotomic polynomials. These are the cyclotomic polynomials that we study. And under this condition, we can show that fx split into linear factors when we take modulo q. So now let's move on to the construction of our error-free key encapsulation mechanism. It's a two-step process. The first one is to construct error-free public key encryption that is CPA secure. Then after that, we apply Fujisaki Okamoto transformation to convert it into a error-free key encapsulation mechanism. So once we have this CPA secure encryption, we sort of get the key encapsulation mechanism almost for free. So let's start with this encryption. Encryption, we work with RLWE. So A is some polynomials. S and E is taken from this set. This set I will explain in more details later. But for now, you can think of it as a set of polynomials with small coefficients. So here we have this B equals SA plus E, because we are basing our schemes on RLWE. Public key is A, D, and secret key is S. So the encryption is like this. Again, we have this set of small polynomials. Just something to remark is that in this encryption we have some randomness when we sample this ZDA. So the encryption is non-deterministic process. When you encrypt even the same message, you encrypt again, you may choose ZDA differently, and it results in different ciphertexts. It's something that is non-deterministic. So the decryption is as follows. Once you have C1, C2, and you have the secret key S, you just compute C as C1 plus C2. And B is something that I will explain later on. So the decryption is about C. C is a element of RQ. It's a polynomial. It has some coefficients. That's called the coefficient Ci. And the decryption is all about the Ci plus B. If Ci plus B is less than Q minus 1 over 2, then the message is 0. Otherwise, the message is 1. You might guess that this Q minus 1 over 2 actually comes from here, because C is this thing plus Q minus 1 over 2 times the message. Okay, so this thing, let's give it a name. Let's call it big E. Right? Big E is equal to this one. And again, it's a polynomial, so it has coefficients. Let's call the coefficients EI. In fact, the strategy to make our scheme error-free is to give a bound on the absolute value of EI. So B, we will take B to be this bound on EI. And then we will take Q to be bigger than 4B plus 1. Why we do it is because once we do these two things, EI less than B and Q bigger than 4B plus 1, then we can show that our PKE is error-free, meaning no decryption error at all. So recall that C is E plus Q minus 1 over 2 times M. Now if Mi is 0, then there is no, this then this part is 0. So Ci plus B is Ei plus B. Ei is at most B, so this thing is at most 2B, and 2B is less than Q minus 1 over 2 because we take Q bigger than 4B plus 1. And then similarly, if Mi is 1, then we can show that Ci plus B bigger than or equal to Q minus 1 over 2. So the conclusion is Mi equals 0 if and only if Ci plus B less than Q minus 1 over 2. But this is exactly our decryption process. So this argument here shows that our decryption is perfect. You always get back the correct plain text. There is no decryption error at all. Right. Now it remains to tell you about this B. Okay, B is a upper bound for all this EI. So this is where the set S n1, T comes in. Okay, so this set is the set of polynomials with coefficient consists of t times any non-zero integer in this interval. Looks complicated, but it's not. So let's look at some example. For example, take n1 to be 1 and t to be equals to 2. Then its polynomials consist of 2 times any non-zero integer in the interval minus 1 to 1. Non-zero integer in the interval minus 1 to 1, there are only 1 and minus 1. And 1 appears 2 times because t equals 2. Minus 1 also appears 2 times. So the polynomials in this set looks like something like this, where minus 1 appears 2 times as coefficients, plus 1 also appears 2 times as coefficients. Using this restriction, we can establish a bound B. This is obtained by carefully studying how the multiplication of polynomials and addition, how they affect the size of the coefficients. So for any n1 and t, this B depends on n1 and t, and rho is this expression here. Yeah, so this is what we come up in our study, in our work. Okay, that's the error-free encryption. And as I said, we can just apply Fujisaki Okamoto transformation to get our key encapsulation mechanism. This is quite a standard technique in this area. So key generation is the same as in the PKE. Encapsulation is this. This is just to highlight that previously the encryption is a non-deterministic process. The Fujisaki Okamoto transformation is basically to convert the non-deterministic encryption to deterministic one by where the randomness ZDA in the encryption previously generated randomly now is no longer random. It's generated by the output of a hash function. So this encryption is no longer non-deterministic. It's now a deterministic process. Okay, the decapsulation is doing the straightforward way. You decrypt back, and then after you decrypt, you do re-encryption. This re-encryption is to check that the ciphertext is generated correctly and not altered. Okay. So this is our key encapsulation mechanism, and we give parameters for various choices of security level and cyclotomic polynomials. This is the security level, quantum security level, 1 to 8 bit up to 256 bit. We can use different choices of cyclotomic polynomials, and this is our n1t. Q is bigger than 4b plus 1. We can compute the public key size, secret key size, and ciphertext size. And we compare for the 1 to 8 quantum security level, we actually compare them with other KMs that is submitted to NIST PQC standardization. And we found that our parameter size is comparable to others. It's sometimes better, like this one is better than Papa Bear, than New Hope, but it's sometimes worse than others, like worse than round 5, for example. But again to remark that most of these schemes they are mostly have decryption failure, and our scheme does not have decryption failure, and the size is still comparable. So just to summarize, we study more option for cyclotomic polynomials, cyclotomic polynomials for RLWE, and then we constructed error-free lattice-based PKE and KM based on RLWE. The thing is that our schemes are error-free, and then we give parameters for various choices of cyclotomic polynomials and security levels. And with these choices, actually the size are comparable to other lattice-based KMs submitted to NIS PQC standardization. So I guess that's all, and thank you.